Good morning, sir.
Good morning.
Good morning, sir. Thank you for joining with us, sir. Good morning to all. We welcome you all for the session 6 on impact of electrical vehicles on global warming. I welcome all the participants and speaker Dr.G.Madhusudhanan to session 6 of ATAL online FDP program, Global Warming and Impacts of Power Electronics Towards Green Technology. Our speaker Dr. Nagarajan is currently Professor in Department of Mechanical Engineering, Head Department of Mining Engineering, Director Center for International Relations and Legal Coordinator, Anna University. He completed BE degree in Mechanical Engineering from Bangalore University in the year 1985. He completed ME in Internal Combustion Engineering from Anna University in the year 1988 and PhD in Alternative Fuels for IC engines from Anna University in the year 2000. He has more experience in the topics of electronic engine management system, control of pollution from IC engines, automobile engineering, renewable energy systems, energy conservation, alternative fuels for IC engine. He has published 164 papers in international journals, 10 papers in national journals, 46 papers in international conferences, 16 papers in national conferences. He is a member of Indian Society for Technical Education, Indian Society for Mechanical Engineers, Compassion Institute USA, Quality Circle Forum of India, Society of Automotive Engineers International USA and SAE India, Fellow Institution of Engineers. He delivered over 300 special lectures in various academic and professional institutions and industries both in India and abroad. Has organized 40 training programs in energy and automotive fields. He visited Malaysia for presenting paper in the international conference in 1999, visited USA for participating in a section officer leadership seminar in 1999. He visited England for visiting universities in 1999, visited Japan for presenting a paper in JSAE Congress and for visiting Honda R&D and University of Utsunomiya in 2005. He visited Singapore for presenting a paper in the international conference in 2013. Visited Abu Dhabi for participating in Indian Education Fair in 2014 and 17. Dubai for participating in Indian Education Fair in 2014 and 17. Kuwait for participating in Indian Education Fair in 2015. Spain on an invitation for participation in European Union project in 2015. Qatar for participating in Indian Education Fair in 2016. Mexico for a joint research program in 2017 and 18. He has received awards from QCFI Outstanding Contribution Award in Educational Sector given by Quality Circle Forum of India, Chennai Chapter 2014. SAEISS Outstanding Contribution given by SAE India Southern Section 2015. He has guided 23 PhD scholars, 6 MS scholars, 105 ME students. He is currently guiding 8 PhD scholars and 3 ME students in the areas of alternate fuels and HCCI, RCCI engines. He has held positions in the past as Treasurer, Secretary and Joint Secretary in SAE International, SAE India, SAE India Southern Section and Compassion Institute Indian Section. He is currently holding the position of Vice President and Treasurer, SAE India. Sir, we are very happy to have you here, sir. And now we request you to deliver your speech, sir. Thank you.
Thank you very much for your kind introduction, Dr. Malathi. Now, what is the timeline for me
Sir, up to 11 o'clock, sir.
Up to 11. Okay, which means can we have about 10 to 15 minutes discussion towards the end of my talk? Maybe around 10:45. Shall I close?
Yeah, sir. Yeah, sir.
And normally, 2 hours continuous listening to the lecture, I always give a break for about 5 minutes. Okay,
Yes.
I will adopt the same thing here because too much of talk from one side, it won't be received properly on the other side, right? So
Yes,
I
sir.
will follow the usual procedure of what I used to do normally in taking classwork. Okay.
With pleasure, sir.
Yeah, thank you very much. Good morning, faculty members and my dear student friends. I am very happy to be part of this faculty development program organized by SRM Valliammai Engineering College under the auspices of this ATAL. And I'm so happy today the entire world is looking at the ways of reducing the carbon dioxide emissions, which is one of the major contributors of global warming. So in that aspect, I'm so happy that the SRM Valliammai has taken a call in organizing this program with the theme as the global warming and impacts of power electronic towards green technology. Okay, so probably as per my clock, it is 7 past 9 o'clock. Maybe around 10 o'clock, I will give a break for about 5 minutes. Probably if you want, if you can ask any questions, or probably we can relax. Both of us can relax for about 5 minutes. Then we will get back. Maybe I will carry forward for another 45 minutes or so, and that will be followed by question and answers. Okay, that's the agenda for my talk today for the next 1.5 to 1 hour and 45 minutes. So what the topic that I had chosen is impact of electric vehicles on global warming. I hope I am audible to everybody.
Yes, sir.
Okay.
Sir. Yes, sir.
You are able to see my screen. I am on the full screen mode.
Sir, we are not able to see your screen, sir.
Oh, you're not able to see. Okay, that's okay. Just a moment. I will. Maybe I wouldn't have uploaded, probably. Yes, I did not.
Sir, I think you have not started to share your content, sir.
Yeah. I'm just doing that. I am not able to.
Okay, sir. Okay, sir.
I will tell you the moment I share it, okay?
Okay, sir. Thank you.
It is not showing up the screen. That's a problem here. What I will do is probably I will log off and get back again, okay? Is that okay?
Yes, sir.
Okay,
It's okay, sir. Okay, sir.
I think I'm not able to see my desktop here. I'll just log off and come back again. Right?
Okay, sir.
Sir?
Yeah.
Sir.
Just connected, but it is not showing.
Sir, can you press the share content, sir, which is next to leave, sir? Share content.
No, that's what I'm just trying to do.
So I'm just.
Yeah, tell me.
Dear participant, please be patient. Sir will join soon.
Dear participants, thank you for staying with us. There are some issues in having the PPT. Now I will share the screen. Nagaraj sir, Dr. Nagaraj sir.
Yeah, you can.
May I share the screen, sir?
Yeah, you can.
Yes, sir. Sir, I have shared the screen, sir.
Okay, fine. Yeah. So maybe then I have to tell you that every time you have to move to the next slide, right?
Yeah, I will be listening the slide and I will be moving, sir. No problem, sir.
Okay, thank you. Yeah, so can I continue?
Yes, sir, you can continue, sir.
Yeah, okay, go to the next slide. Okay, so what is it I am going to talk to you about for the next 1.5 hours? As I said before, you can see that maybe I will give a little bit of introduction to what is automobile. I know that it is a blend of mechanical, electrical, there may be some electronics engineers, maybe some automobile engineers. I'll be touching mostly on, you can see the critical aspects of EVs, the importance of power converters, right, in controlling the electric vehicles. Maybe I'll start with battery fundamentals, battery management system, battery heating and cooling system, battery charging, electric motors, then transmission system, regenerative braking system. Then, of course, we'll talk about EMI, that's electromagnetic interference, and maybe I will be concluding with that. Yeah, next slide. Next. Yeah, so probably those who are not aware of an automobile, so if you have an automobile and if you don't have any frictional forces, if there are no wind resistance, and probably if you have somebody pushing your car from one place where you want to move, and the car would move freely, and where you want to stop, and if you have your friends or other family members, they can just stop the vehicle. But it is not happening in nature, mainly because of the reason that there are various forces, those are acting, right? Various forces, those are acting on the automobiles. These forces are, okay, maybe I will just, okay. You're able to see the pointer? Yeah, so you can see that vehicle has got to move in the forward direction, that is towards the right to you. But what happens actually, you'll find that the automobiles will be subjected to rolling friction as a result of friction between the tire surface and the road surface. And there will be aerodynamic drag, like, whenever you move forward, you would find that the wind will be blowing onto the automobile body. So, and also you would find that there'll be inertial force during acceleration. Maybe as engineers, probably in engineering mechanics, you might have come across that, we make a force balance. So wherein you'll find that all the forces acting on the right hand side will be equated to all the forces acting on the left hand side. So if that is the case, you just click on to the next one. Go to the next one. Yeah, so forward force is equal to the rolling resistance plus the aerodynamic resistance and the inertial resistance. And of course, if an automobile goes through a gradient, and there will be a gradient resistance as well. So which means that an automobile has to overcome these various resistances for it to move forward or propel forward. Next slide. Yeah, for doing this job, you can see that we have a power plant that is sitting inside an automobile, and that's what you can see here. What is shown in red color, that's the engine. So it is this engine, right, that does the job of producing power, and that power is used to be transmitted to the wheels for setting the wheel in motion. So it is this power plant what we are going to talk about today. Next slide, please. Next slide, please. Yeah. So if you look at an internal combustion engine, we need three components, namely the air, fuel, and spark, very similar to what human being needs. We need air and we need food. So the food for the engine is the fuel, and we need energy. So engine also requires energy. That energy is obtained by burning the fuel inside the engine combustion chamber, like petrol and diesel, right? So basically, if you look at all these fuels, they have hydrogen and carbon that is present in it, and we set in air, which has oxygen and hydrogen. So what we try to do is, probably must have studied in chemistry, where there'll be chemical reactions that will be taking place inside the internal combustion engine, where there will be decomposition of this hydrocarbon that will be taking place, and hydrogen will be combining with oxygen to form H2O, and the carbon will be combining with oxygen to form CO2. Nitrogen is supposed to be inert. You would find that nitrogen will be coming out in the exhaust as it is. So if the products, those are coming out of the engine exhaust, contains only H2O and CO2 and N2, we say that the combustion or the burning is complete, or the combustion is perfect. Okay, and these are all harmless emissions. H2O, CO2, and N2 are harmless emissions. Okay, next slide, please. Okay, but in the process, what happens? You will find that we not only get H2O, CO2, and N2, but you find that we also get carbon monoxide, CO. We do get partially burned hydrocarbons, and we do have oxides of nitrogen emissions. Now, all these three pollutants are harmful to the life of the human being, right? And if you take the case of diesel engines, it has another serious issue of emitting what is known as a particulate matter or soot, right? So out of these, you would find that CO2, though it is a harmless emission, and you know CO2 is a global warming gas, and because of the presence of CO2 in the atmosphere, you find that the average temperature of our atmosphere keeps increasing year by year when we dump more and more CO2, and that's the reason why today people have been talking about global warming for the last 20-25 years, and that continues to be a topic for the next 20-25 years, because we need to reduce this global warming effect. Hence, all the automakers, and including the people who are working on energy resources, they all work towards reducing the CO2 emissions. And in that aspect, that's the reason why you find that today people talk about replacing these internal combustion engines powered by gasoline, that is petrol or diesel, right, to be totally replaced by electric motors for driving the vehicle, so that we can totally do away with carbon dioxide emissions. Do we really do that when we go for electric vehicles? That's what we are going to see as part of my lecture. Next slide, please. Yeah, so if you look at this, you can see that I have collected some data. So of course, it's a very old data, maybe about 35 years back, but still, maybe the quantity may be varying today, but still you will find that it is really mind-boggling. So wherein you can see that a medium-sized car, which can have a life of about 10 years, which can make about 13,000 kilometers per year, with a fuel consumption of approximately 9 kilometers per liter, will produce about 325 kilograms of carbon monoxide. Unburned hydrocarbon, 36 kilograms. Oxides of nitrogen, 47 kilograms. And see the carbon dioxide, it is 44,000 tons. Carbon dioxide is 44,000 tons. So this amount of exhaust gases means that we pollute the atmosphere to an extent of about 1 million meter cubed of air. 1 billion is 100 crore. So 100 crore meter cubed of polluted air would be there, right? Just by one medium-sized car. Okay, next slide, please. Next slide, please. Next slide, please. Yeah, so I have given some, India's liquid fuel consumption here. You can see that we consume about 112 million tons. This data as of 1819. Okay, just go back, please. Go back, please. Yeah, so you can see that India emits about 97 million tons of unburned hydrocarbon emissions, carbon monoxide 1,190 million tons, oxides of nitrogen 192 million tons, and carbon dioxide 3,52,000 million tons of CO2 is what has been given off to the atmosphere by India by consuming 120 million tons of petrol and diesel put together. So this is only from the transportation sector. Okay, so you can imagine the power plant in India uses about 60 to 65% of fossil fuels for producing electricity, and you can imagine that will be emitting billions and billions of tons of CO2 and other pollutants into the atmosphere. Okay, next slide. Well, this electric vehicle is not new. You can see that even in 1900, right? So it used to be a very, very, vehicle which could be used only by the elite people like Thomas Edison, Rockefeller, Clara Ford, wife of Henry Ford, because of the reason that the automobile used to be very quiet and it will be, there won't be much of a vibration. And also, IC engines will be polluting, okay, right? So which means that not all can afford to buy an electric vehicle at that point of time. That's about 120 years ago. Next slide, please. Well, you can see in 1900, there used to be a lot of horse-drawn carriage, and out of that, there will be only one automobile. You can see that the one that is given in red color, one automobile. But in about 13 years' time, you can move to the next slide. In about 13 years' time, you would find that the total scenario change, wherein you will find that there are so many automobiles, and there's only one horse-drawn carriage in 1930. So what I'm trying to say is, electric vehicle is not new, but because of the advancements in technologies in electronics, electric motors, and power converters, controllers, and so on and so forth. And today we will talk about electric vehicles, right? Okay, next slide, please. Yeah, so electric vehicle is not new. I don't know how many of you are aware that, diesel locomotive, the trains which used to be run by diesel engines, right? Actually, diesel engine does not power the wheels directly, but diesel engine actually drives an alternator, and the alternator produces electricity, and that electricity is utilized in driving the wheels by means of these traction motors. So actually, diesel locomotive is an electric vehicle. Okay, next slide. Right, so if you look at the architecture of electric vehicle components, it's very simple, wherein you can see that it's got a motor, there is no engine, battery, of course. In both the cases, even engine powered automobile, we have batteries, but electric vehicle components, battery is the heart of the system. We do have a transmission very similar to what we used to have in the case of conventional automobiles, and of course we have motor controller and the vehicle controller. Okay, next slide please. So the architecture, if you look at this, you would find that it will be very simple. It's very simple. So where you can see that there is an electric motor that is sitting here, right, and that will be supplying power to the wheels. The electric motor is supplied from energy from the battery, and as we know, battery can store only DC, and you find that today we make use of alternate current motors. So we have an inverter for converting this DC into AC, thereby AC power is supplied to the electric motor for driving the wheels. Next slide. Yeah, let's talk about battery fundamentals. Next slide, please. Yeah, so there are two major things that we need to look at as far as the electric vehicle is concerned. Right, when we talk about the conventional automobiles, we talk about torque and the power. We want that torque peaking at lower speeds and the power peaking at higher speeds. Right, so here we talk about, because whenever we talk about electricity, we talk about voltage or the potential difference or the EMF, electromotive force, right? So voltage is the driving force that causes the current to flow from one place to another place. Okay, voltage is very important. We will come to that a little bit later. Yeah, next slide, please. And the next one is current. Current is the rate of flow of electric charge, the rate of flow of electrons, whatever we call. So as far as batteries are concerned, it depends on the electrochemical reaction that takes place between two electrodes, namely the anode and cathode, one functioning as the positive, the other one functioning as the negative electrode. So voltage and current are two important things that we need to have in mind when we talk about electric vehicles. Next slide, please. Yeah, so why we are particular about voltage and speed? So higher the voltage, the faster an electric vehicle can go. So if you want to travel at higher speeds, then maybe you need to have high voltage. And if you want to accelerate the vehicle, let us say you're moving from 40 kilometers per hour speed to about 60, or from 60 to 80 kilometers per hour, then you may need a higher current. So for acceleration, we need current, and for speed, we need voltage. That's the reason why I said that when we talk about electric vehicle, then voltage and current are two important parameters that we need to look into. Next slide. Yeah. So if you look at this slide, you can see that actually we have you can see that the current that is required in the case of an automobile would be varying exponentially with respect to the speed. Okay, exponentially with respect to the speed. You can see that as the vehicle speed increases, the current requirement is higher. Like for example, if you want to travel at about 80 kilometers per hour speed, you can see that the battery should supply a current of about, say, 100 amps. And typically the voltage would be around 400 volts approximately. Now, if we try to calculate the power, probably the mechanical and automobile engineers will know that power is equal to 2 pi nt by 60,000 kilowatt, right? So here in terms of electricity, the power is computed using the product of voltage and the current. Voltage is 400, and if the current is 100 amps, now you can see that it is 40,000. So voltage into current is watts, right? And 40,000 watts, which means that it is 40 kilowatt. So it means that when the vehicle speed is about 80 kilometers per hour, the power that is consumed is about 40 kilowatt. Okay, so higher the speed, more would be the current that will be consumed. But what happens when you increase the speed, the range that can cover, right, that could be covered by the automobile will decrease. Okay, next slide. Yeah, this is what I said. So power is work done per second. Okay, as with the internal combustion engines, we know as speed increases, we need to supply the engine with more fuel. So very similar to that, the faster the electric vehicle moves on, so we need to supply more power. That power is supplied from the battery. Okay, right. And that depends on the voltage. Next slide, please. Yeah. So rated voltage, this is very, very important. Like, so the commonly used chemistry, battery chemistry in electric vehicle is lithium ion. Like what we use in the case of a mobile phones, it is lithium polymer, which also has a rated voltage of about 3.75 volts. Right? So rated voltage is the average voltage, right, over a full charge or discharge cycle. So the rated voltage of any lithium ion cell is 3.75 volts, but normally you will find that it will be varying from about 4.2 volts to about 2.5 volts. Right? The voltage will never go down below 2.5, and the voltage should never go beyond 4.2 volts. So on either side, you would find that the battery or the cell will become weak when we overcharge and when we undercharge for a longer duration. Okay, next slide. Right, so energy. So when we talk about energy, energy is like mechanical terms. That's nothing but the rate of doing work or the capacity to do work. Right, so energy, rate of doing work, we know the work is done by means of power and it is rate, so multiplied that by time. So here the power is V into I, so we have V is voltage, I current in amp, that's what is given here, VA, and time is given in terms of hour. So as I told you before, V into A is watt hour, right? So the energy is given in terms of kilowatt hour. Like what we have at home in the case of electricity units, where we consume energy, that is electric energy, and we know 1 kilowatt hour is 1 unit, and we are paying for the units what we consume. So it is energy, right? Now the energy of a cell would either be increased by current or by voltage. We will come to that a little bit later. Next slide, please. Yeah, so if we look at this, you can see that, as I told you before, like internal combustion engines, right, the electric vehicle also needs energy, but here energy we give it in terms of voltage and the current, and depending on the capacity of the vehicle. Like for example, if you take the case of a two-wheeler, maybe you must have come across that two-wheeler, we start from 50cc engine like TVS 50 and a maximum of about say 500cc as far as India is concerned in the case of bullets. But otherwise, if you take the case of passenger cars, typically the capacity of the engine would be varying from about say 1000cc to about 2500cc, and a convex, that is a commercial vehicle, the capacity would be varying from about say 1500 2000cc to as high as about 4500 5000cc. So the more the capacity, more would be the energy that would be supplied, so that it will be producing more power for carrying more weight. Like for example, the two-wheelers can carry only 2 people, cars can carry only 4 people, buses can carry only about 50 people. So you can't have too many people loaded on a two-wheeler or a car or on a bus, because of the reason that the power plants are designed only to produce a certain amount of power. So very similar to that in the case of electric vehicles, depending on the size, the capability of carrying the load, you can see that the amount of energy that is consumed by each one of the vehicle varies. obviously a two-wheeler should consume lesser energy. So it will be consuming anywhere between 50 to 100 watt-hour per kilometer. Cars would be consuming anywhere between 150 to 250 watt-hour per kilometer. Right? And medium commercial vehicle will be consuming anywhere between 300 to 400 watt-hour per kilometer. So you can see that actually very similar to what we consume electricity at home for making use of our electrical gadgets. So the electric motors will be consuming energy, right, for the automobile to be driven on road. Okay. And of course, you can see that I have given the range here starting from 50 to 100, 150 to 50, 300 to 400. But the range of vehicle depends on the speed. Higher the speed, more will be the energy that is consumed. Okay, then per kilowatt hour rating. So it depends on the capacity of the battery. We will come to that a little bit later. The driving conditions, right? Sudden acceleration and deceleration will result in losing a lot of energy. Suppose if we are driving on a hill, it will be consuming more energy. If the wind blows against the automobile, there will be more of wind resistance. So the automobile will be consuming more energy. If the vehicle weight is more, it will be consuming more energy. Temperature is higher, your driving styles, and several other factors, right, determines the range of the vehicle. If you want more range, then you have to maintain a constant speed, right? There is no rapid acceleration, deceleration. You should not add too much of weight. Okay, so driving habit, which means anticipating signals, all these things will increase the range of electric vehicle. Okay, next slide, please. Yeah, so if you look at this slide, of course, you can just check in the internet. I have taken it from the internet only. Okay, so you can see that although we talk about, of course, we make use of nickel cadmium, nickel metal hydride for various other applications like, in TV remote cells, right, or air conditioner remote cells. But today, if you look at the electric vehicles, we make use of only lithium, right? Lithium ion cells or batteries, because of the reason that it is the lithium ion battery or the cell which has got both higher specific power as well as higher specific energy, right? So compared to that of the lead acid batteries, which are commonly used for supplying power in the automobiles, you would find that the specific power and the energy is approximately about 1.5 or 2 to 2.5 times more than that of the lead acid battery. Okay, right. Next slide, please. Yeah. So what is a battery? Battery, as I told you, it has got two electrodes. It's very similar to that of maybe what I can say is that electrolysis process where you have two electrodes. Okay, where electrolysis, the purpose is different. So here what happens actually, there is exchange of lithium ions, right, and electrons between the anode and cathode. So lithium ion exchange takes place between the anode and cathode, and the electrons will be moving through an external circuit. So it is these electrons what we are interested in making the current to flow through. So we are making use of this current for maybe for charging the battery or for driving the motor. So accordingly, we need to choose the electrode materials that gives the highest potential. So if you take the case of lead acid batteries, and we know a lead acid battery can give, a cell can give only a maximum of 2 volts. Even if you take the case of AA batteries, what we make use of it for our remotes, it can give, each cell can give a maximum voltage of about 1.5. But whereas lithium ion cells can give a maximum voltage, as I told you before earlier, it can give about 4 to 4.2 volts. So that's the reason why lithium has attracted to be one of the main materials for use in the automobiles, in particular the electric vehicles. Yeah, next slide, please. Yeah, so we know again, like lead acid batteries, where there'll be, charging and discharging, which means there'll be reactions that will be taking place in the case of lead acid batteries. But here you will find that there will be no chemical reaction, unlike in the case of lead acid batteries. But what happens actually, there is electron movement, as I told you before. So during discharging, you will find that the lithium ions will be traveling from the negative electrode, that's anode, to the cathode, and during charging, and you will find that the lithium ions will be moving back from the cathode to anode. So in the process during discharging, what happens, electrons will be moving towards the external circuit, and you would find that the electricity could be used. Okay, next slide, please. So that's the principle of a battery. Yeah, this shows of course, you can also get a lot of information about this from the internet. So you can see that we make use of so many materials here. In the case of lithium ion batteries, like we have NCA, that is nickel, cobalt, aluminum oxide. Then we have NMC, nickel, manganese, and cobalt. LMO, that is lithium manganese oxide, and lithium LFP, that is lithium iron phosphate. So if you look at all these things, you would find that all these materials have higher specific capacity and higher specific energy. And today, different vehicle manufacturers make use of NCA of different composition, NMC of different composition. We started with 622, that is 60% nickel, 20% manganese, 20% cobalt, and today it is 811, that is 80% nickel, manganese 1%, 10%, and cobalt 10%. So like this, different auto manufacturers or different battery manufacturers make use of different chemistries. Okay, next slide, please. Yeah, this again, as I told you before, you can see that if you make a comparison of the lithium ion batteries that is shown on the last column with that of the nickel metal hydride, nickel cadmium, and lead acid, you would find that the lithium ion batteries are superior in all aspects in terms of specific energy. Like as I told you before, you can see that lead acid battery, it is about 30 to 40 watt hour per kilogram, and it is a lithium ion, it is 130 to 200. Okay, and energy density is 60 to 90 watt hour per liter, but whereas in lithium ion it is 180 to 320. Specific power is 250 to 600 kilowatts per kg. Lithium ion, you can see that it's about 1,200 to 4,000. And not only that, the most attractive point from in the case of lithium ion batteries, you can see the last row, the nominal cell voltage, the maximum what we get is 3.75 in the case of lithium ion. But whereas you can see that none of the other batteries, right? None of the other batteries are able to give even 1.5 volts, except in the case of lead acid, which I already told you before. Next slide, please. Yeah. Now, as I told you before, each cell can give a certain amount of current, certain voltage. Like even if you take the case of a TV remote control unit, you would find that we need to insert two cells of 1.5 volt each. Right? These cells, because the remote requires about 3 volts voltage. So what we try to do here is two batteries are placed in series so that 1.5 plus 1.5, it will give an output of 3 volts. Okay, so if the cells are placed in series, you would find that the voltage could be added up. Or if each cell can give 2 volts, you can just multiply by the number of cells those are placed in series and you will get the total voltage. Just to give an example, if you look at it, you can see that there are 4 cells shown here on top, and each one is capable of giving 3.6 volts. Obviously, it means it's a lithium ion cell, and each one is capable of delivering about 3,400 milliamp hour. Okay, 4 cells, so 3.6 volt into 4, it is 14.4 volts. So which means that when we have 4 cells placed in series, in this case, we get a voltage of 14.4 volt. But you can see that the current remains the same. Okay, the current is only 3,400 milliampere hour. But out of these 4 cells, in case if one of them goes off, it does not give the full voltage, you will find that proportionate to that, there will be a drop in voltage. You can see instead of 10.8 volts, now it has become only 10 volt, because 3.6 volt has dropped down to 2.8 volts. So full voltage is not available. So there is a faulty cell. Next slide, please. So we talked about placing the cells in series in order to get a higher and higher voltage. And if you want more current, then we need to place the cells in parallel. So if you look at the first one on the left hand side, you can see that it shows the same lithium ion cell, 4 numbers placed in parallel. Okay, now you can see the voltage remains constant, that is 3.6 volt remains constant. It is only the current that will get added. So it is 3,400 milliampere hour into 4, that is 13,600 milliampere hour. So if you want, what I'm trying to say here is, if you want more voltage, place the cells in series. If you want more current, place the cells in parallel. Here again, in case if there is a faulty cell, and there will be a proportionate drop in the amount of current what it can give out of these 4 cells. Okay, but you might ask a question, okay, when you want more voltage, I need to place the batteries and cells in series. And if I want more current, I need to place the batteries in parallel. But if I want both higher voltage and higher current, like in electric vehicle applications, what is that we need to do? Go to the next slide, it will show you that we need to place the cells both in series and parallel. So the more the number of cells what you have in series and parallel, the more voltage and current what you get. Now, for example, if you take the case of Tesla, you can see that I have shown you Tesla commonly uses an 80 kilowatt hour battery. Of course, nowadays it comes with the Tesla S3 model. It comes with 100 kilowatt hour battery also, which has something like about 8,156 cells. And you can see that most commonly used battery pack is 85 kilowatt hour. And you can see that it has got 7,104 cells with 96 cells placed in series. So which means that 96 into, let us take it as 100 cells into approximately, let's say each cell is giving about 4 volt output. So the total battery pack will give a voltage of approximately 400 volts. You understand? And 74 cells are placed in parallel, which means 74 into 3,003.4 will give you the total amperes that it can give. So in this way, you can have the cells placed in series to get high voltage, cells placed in parallel to get higher amperage. And if you want both, you need to have both the cells in series as well as parallel. Next slide, please. Yeah, so we talked about cell, okay? So each cell is capable of giving about 4 volts. So if you want 100 volts, 400 volts, which means you need to have 100 cells placed in series. Okay, now these cells are packed in a system, and that system is called as a module. Okay, so each module will have a certain number of cells placed in series or parallel, and there'll be number of such modules that will be available. So the entire system is called as a battery pack. So the battery pack will have different modules, and the modules will have different number of cells in it. Next slide, please. Next slide, please. Yeah, this shows the Nissan Leaf vehicle structure. Nissan Leaf is one of the very popular models in the case of electric vehicles or electric automobiles. So wherein you can see that we have, it makes use of 48 modules, right? It makes use of 192 cells, and each module has got 4 cells. So 4 into 48, that is 192 cells. Okay, next slide. Next slide, please. Yeah, this is the battery pack of Volkswagen. So you can see that in an automobile, it is very easy for us to place the battery pack on the floor of the automobile, right? So which means that actually we will be keeping our foot on top of the battery. Okay, next slide, please. Yeah, this is just to give an information. You can see that I have given some, of course, it is taken from the net. The source is Battery University. So you can see that I have given some of the very popular electric vehicles which are available on the world's roads: BMW i3, GM Spark, Honda Fit, Nissan Leaf, Mitsubishi, Ford Focus, Mercedes. Sorry, it is Mercedes, not Mercedes. Okay, Tesla. So what I would like you to have a look at it. You can see that it has got different capacities of the battery. You can see that the capacity ranges from 16 kilowatt hour to about 75 kilowatt hour in the case of Tesla 3. So you can see that Tesla is the one among all the vehicles. You can see Tesla is the one that consumes lesser energy of about 150 watt hour per kilometer. Whereas you can see rest all on an average consuming anywhere between 180 to 200 watt hour per kilometer. So what we are interested in this is we need to reduce the power consumption per kilometer drive so that we can increase the range for the given battery. So what is it I am trying to say here is, if you look at the Tesla, which has got a 75 kilowatt hour battery, now we can see that it consumes about 150 watt hour per kilometer, right? If we make this, just to give an example, if we make this 50 kilowatt hour per kilometer, that is, if we can design the system in such a way that the Tesla vehicle can consume only 50 watt hour per kilometer, then the range that can be covered with the same battery would be about 3 times that of 496, which means that it can cover about 1,500 kilometers. 1,500 kilometers. Okay, next slide, please. Okay, this is just to give an idea. You can see that per kilowatt hour of a battery capacity, you can see that it requires a lithium of about 2 kilograms and 75 kilowatt hour or 100 kilowatt hour, and you can imagine that it requires about 200 kilograms of lithium, and each kg costing 2,400, and you can see that per kilowatt hour, right, it cost anywhere between 12,600 in 2018, and you can imagine in 2010 it used to cost about 86,400. Okay, and the cost is coming down. Okay, right, next slide, please. Yeah, moving on to the battery management system. We talked about battery. Moving on to the battery management system, which is very, very critical. This is where actually the power electronics plays a very significant role. Next slide, please. So we talked about the beauties of batteries in giving higher voltage and higher current that is required for increasing the speed of the electric vehicle or for accelerating the electric vehicle. But we do have a lot of problems in batteries. oxidation of cell components, cathode will be breaking down, there'll be pressure buildup, electrolyte might break down, separator between the electrodes will be melting, and there may be over temperature, and we may supply with over current, over voltage, low temperature. Now, the battery must be maintained in such a way that we do not encounter any of these problems. Okay, next slide, please. Right. One of the critical problems in the battery is the thermal runaway. What happens actually, you would find that there will be an increase in temperature. Right? So increase in temperature will cause more reactions. It is like, temperature and the reaction rate in chemical reactions. If the temperature increases, we know that the chemical reactions are going to increase. If the chemical reaction increases, the rate of reaction will increase. If the rate increases, temperature will increase. If temperature increases, the rate of reaction will increase. So in this way, you would find that increase in temperature would cause the situation to become worse and worse, ultimately resulting in causing some type of destructive thing happening in batteries, which means that it will be releasing more and more energy. This is a very serious issue. I don't know how many of you have come across this, even if you take the case of of course, nowadays, I think all these things are built in the mobile phones. If you take the case of olden day batteries, they were never used to have some kind of over voltage protection. If you overcharge the batteries, or if you charge the batteries beyond its normal voltage, or if you charge it for a very long time, even after reaching 100%, right? What happens? You will find that the battery will become bulged. That's polymer. It will very, very easily get bulged. But nowadays we have all these, softwares, which will automatically cut off the moment it finds that, okay, your 100% charge has been attained. Okay, next slide, please. So thermal runaway, that is heating. Next slide, please. Yeah, so what is that we need to do? So we need to limit the charging current. Now, even if you look at the mobile phones, the adapter, it will say that, even if you take the case of a mobile phone charging, it will say that the output or the input current to this mobile should be only 0.5 amps or 1 amp. In case if you use an adapter which can supply 2 amp of current, it will damage the batteries. Today we have all these protection circuit, wherein even if you make use of a 2 amps adapter, you would find that the software will not permit, right, more than 1 amp current to be passed on to the battery for charging. Okay, next slide, please. So what I'm trying to say is, if you increase the charging current, it will result in overheating. Charging temperature. The temperature of the battery should never be lower than 0 degrees Celsius, or should never be greater than 45 degrees Celsius. Okay, and the typical operating temperature of the battery or cell should be only about 35 to 45 degrees Celsius, and not more than that. And discharge current. This also requires some kind of a protection, because of the result that there will be some short circuiting that will be taking place if we have a rapid discharge of the current. Next slide, please. Over voltage, I think I already told you about it. And overcharge protection, right? So we need to have all these things. Of course, you will find that even in most of the smartphones, you have all these things inbuilt. Even in smartphones, you have all these. Reverse polarity protection for when you charge the batteries, in case if there is any reverse in polarity, then that will affect the electrodes. So we don't want that to happen. So the system will identify that there is reverse polarity. So that protection will be done. Over discharge. Discharge should not be less than, the voltage of the battery should never go lower than 2.3 volts. That's the reason why, even if you look at our smartphones, you would find that, up to 10% battery charge, you'll find that it will be slowly draining off. Okay, from 10 to 5, it will be much more slower. And all of a sudden, you will find that the mobile will go off. That is because of the reason that the over discharge protection has already been built in this. Because the battery voltage should never go down 2.5 volt if it's a 4-volt battery. Okay, next slide, please. Yeah, over temperature. So you can see that if the temperature is more than 100 degrees Celsius, it can cause irreparable damage. Next slide, please. Yeah, so what do we have? So if you look at this, this is where the power electronics plays a very, very significant role in the battery management system. So it has got monitoring components. It has got one or more power conversion stages, and of course, very intelligent controllers or embedded processors. I'm not going to get into the details of that. Probably I'll be just have a surface kind of a treatment in order to make you understand how the power electronics plays a significant role in managing the battery in order to prevent the battery from encountering the problems which I described earlier. Next slide, please. Yeah, so intelligent cell monitoring. So you would find that low voltage. We have already seen that low voltage or high voltage can lead to very serious issues like thermal runaways. Next slide, please. So the cells require continuous monitoring. So for this, a BMIC, a battery monitoring integrated circuit, or cell balance monitors the voltage of each and every battery cell in a module. Now you can imagine, probably might ask a question, why the cells are packed in modules into battery packs, because if you have 400 cells, it will be very difficult for every cell to be monitored, and that is where we go for modules. So each module will have, say, about 45 batteries, and each module will have a BMIC, okay, battery monitoring integrated circuit, so that each battery cell can be monitored. Then we have a cell management controller, right, and also a battery management controller. So you can see how many controllers are there in just managing the battery. Next slide, please. Why we need to control all these things? So you would find that normally, in general, when you find that one cell has become weak, you always need to replace both the cells. Okay, otherwise what happens, if a weaker cell is replaced by a newer cell, the cell which is already in use, right, that will be discharging very rapidly. That's the reason why we always say that whenever you make use of two cells, if one cell goes off or one cell becomes weak, then you have to replace both the cells together. Otherwise, there will be cell imbalance or unbalance. Okay, that will lead to variation in voltage levels. We will come to that later on. Why? Next slide, please. So problems of cell unbalance, you can see, as I told you before, you can see that thermal runaway. What happens? Let us say in a pack of 4 cells, right? One cell is 3.5 volt, the other one is 3.2 volt. What happens? Charging will continuously taking place in all the cells. But what happens? You would find that 3.5 volt cell will continue to be charged, though it would have attained 3.5 volt, but 3.2 volt, right, still it wouldn't have come to 3.5 volts. So what happens in this case, both 3.2 as well as 3.5 volt will get continuously charged, though 3.5 volt has already attained the rated voltage. So what happens in this case, because of overcharging of this one cell which has already reached 3.5 volt, the temperature would increase. So that overcharging would result in causing thermal runaway. Okay, next slide. So what happens? We talk about thermal runaway. When you overcharge the batteries, you will find that the batteries will get degraded very much faster, to an extent of about 25 to 30%. Even if you charge the voltage by battery from 4.2 to 4.25 volt, just 0.5 volt increase in voltage will result in reducing the battery life by about 30%. Next slide, please. Yeah. So incomplete charging of pack. Okay, so what happens? You would find that initially we will have all the cells, completely charged. But what happens, you will find that as we operate, as we make use of the battery cells, you would find that because of rapid charging and discharging, you will find that there will be extension of the cell. Next slide, please. So what happens as the batteries in a pack get older and older? This is just to give an idea that you can see that different cells have different energy levels. Some of the cells have become very weak, some cells have become weak, and some cells are healthy. Like the center one is very healthy. Okay, the extreme and the fifth one, and the sixth one are okay, but you can see the fourth one and the ninth one are very, very weak. So we should not have these type of things. Okay, next slide. So what happens while charging the batteries? This is one of the issues, right? While charging the batteries, though we want all the cells to attain 3.5 volts, if two cells charge it to a level of 3.5 volt, you will find that automatically the charger will be cut off, which means that the remaining cells will not be attaining full voltage. So it will attain only about 90% voltage. That's what you can see. Except the two cells which are shown at the center, you can see that the cells have charged faster. And you always have this in mind when you have a healthy cell and when you have a weak cell. Whenever you charge it, you will find that the weaker cell will get charged very quickly. And whenever discharging takes place, you will find that the weaker cell will charge very quickly. Okay, so what happens likewise, when battery discharge takes place, you would find that if two batteries which are good, right, discharge will be taking place. If the discharge takes place fully, automatically the charging will cut off, which means that you can see the remaining cells, the bottom green patch, what is shown, still each one has about 30% of charge that is present in it, and you would find that they remain unused. Okay, so in this way, you will find that we are not in a position to make use of the complete energy available in the battery pack. Next slide. Yeah, this is just to show, you can see that we waste the energy in certain cases. On the left hand side, you can see that discharging takes place. One cell has totally discharged, and on the right hand side you can see charging. You can see one cell that is shown in green color is totally charged, right? So which means that in this case you can see that we are not making use of the energy that is available in the remaining cells. Okay, next slide please. Yeah, so I think I have taken more than 45 minutes. It's time that we need to have a break. So if you have any question to ask in the meantime from what we have already discussed, maybe I'll be glad to take it up. Those who would like to ask questions can turn on the mics.
Dear participants, if you have any queries, you can unmute your mic and you can ask.
Hello, good morning, sir.
Good morning.
Sir, can you elaborate the performance of the battery due to acceleration and deceleration in traffic?
Okay. It's not a question of deceleration. So what I'm trying to say here is, like, for example, even if I don't know whether you own a two-wheeler.
Sir, four-wheeler.
So you have a four-wheeler, right?
Yeah.
Okay. Now you are moving on a road, right? 1 kilometer ahead of you, you see the signal has turned red. You understand?
Yeah. Yes, sir.
What do you do?
So we remove that acceleration. We reduce the that is acceleration.
No, I want a honest answer. Do you do that?
Pardon.
Huh?
Hello, sir.
I want a honest answer from you. Do you do that? Do you remove your foot from the accelerator pedal the moment you see a signal?
No, gradually we remove, sir.
So which means you are not removing your foot from the accelerator pedal.
Yeah.
Okay. So what is that you are trying to do? For powering an automobile, as I told you before, you need energy. Where do you get this energy from? You are supplying either in the form of petrol or diesel. While accelerating, the engine consumes more fuel because you need more energy.
Yeah.
Okay, you are spending energy for accelerating. What is the point in suddenly applying the brake? You are wasting all of the energy.
Right, absolutely.
You understand? That's why we always say that always anticipate braking, anticipate signals. Don't keep accelerating until you reach the junction of the road. And there you jam the brakes. You are wasting a lot of energy. Now here, when we talk about electric vehicle, you are drawing more charge while accelerating. Okay.
Sir, my question is, in heavy traffic, frequent braking is required.
No, that is what I am saying. That is why I said it depends on the driving style or habits as well as the driving conditions.
Yeah.
Okay. So what I am trying to say, whether it is electric vehicle or IC engine powered vehicle, don't rapidly accelerate or decelerate. If the traffic is heavy, right, you move slower. You don't accelerate the vehicle in such a way that, the moment you accelerate, suddenly you will have to jam the brakes. Don't do that. That's what I'm trying to say. Anticipate. Always have this in mind. You anticipate. If the traffic is heavy, you drive your vehicle accordingly. Understand?
Yes, sir. Yes.
Yeah.
Yes.
Yeah.
Sir, one question asked from chat.
Yeah.
Paul. He asked that how an onboard controller is deployed in real time.
How onboard
controller is deployed in real time?
Say it is everything is on board today. Even if I would like to just share, like even if you take the case of the passenger cars, what we have today, right? There are, I would say, the most modern automobile has about 80 to 100 microcontrollers inbuilt in the automobile. Each electronic control unit manages, like one managing anti-lock braking system, the other one global positioning system, one air conditioning system, one transmission system, one steering system, one fuel injection system, one ignition system. So like this, we have the controllers. Okay, we have controllers, right, which are present in the automobiles and which monitors these things very closely. Okay. Is the answer satisfied for the student who posed this question? Yeah. Anybody else who would like to ask question?
Any participants want to ask any questions? So one more question from Sharwani Pal.
Yeah.
Then it is a global control or a local control? If so, the power consumption of controller is in the limits.
Yeah, nowadays, see, the controllers are designed in such a way that it consumes less power, right? So, okay, when we talk about electric vehicle in particular, when it can give a very high voltage of about 400 volts, right? Just by making use of cells. And of course, with the power converters, today we can go up to about 800, 900 volts whenever, on a very rare occasion, right, where there may be a requirement of about 800, 900 volts. Then, of course, only in such situations you will find that the power consumption of these controllers would be more. So otherwise, normally, all these electronic components, when compared to that of the electrical gadgets, the power consumption, we talk about only in very, very low. Like, for example, even if you take the case of mobile phones, consume something like about, it's 3.7 volts and 2700 to 3000 milliampere hour. So we talk the current consumption only in milliamps in mobile phones. So like that, all these electronic gadgets, the maximum voltage what we talk about in all these things itself is, controllers and all, it's only about sensors and other things, it's only about 5 volts. So current consumption is not significant. Of course, people are working towards reducing this current consumption further. Okay, current consumption is not an issue as of now. Yeah.
Thank you, sir.
You're welcome. Yeah, if there are no questions, probably I will continue for another half an hour. It's 10:25 as per my clock. So we talked about thermal runaway, a lot of issues, weaker cells, charging quickly, discharging quickly. And you would find that the moment one cell gets charged fully, the entire charging circuit gets cut. Or the moment one cell gets totally discharged, again charging happens, though we have the remaining cells still having certain amount of energy. Now, all these problems could be again overcome by certain technologies, again making use of electronics. So that's what is cell balancing methods. So I am not going to get into the details of this because I am only a mechanical engineer working in internal combustion engines and automobiles. But I have a little bit knowledge about all these things. Maybe I'll be just touching upon one or two of this, right? Just to give an idea on what beautiful feature, right, it has been inbuilt in the battery management system. So we have in the cell balancing method a passive cell balancing, where there will be shunting of the charge between cells, and there are integrated circuits, right? So for balancing the cell, and also there will be charge limiting. Next slide, please. Yeah, so we do have active cell balancing. So where there will be shuttling of the charge, making use of flying capacitors. Then, of course, like what we have, the inverters, right? Inductive converter, buck and boost method. Then we have flyback based inductive converter. And of course, finally, the lossless balancing, meaning that there won't be absolutely any loss from the cells. Next slide, please. Yeah, this is one of the commonly used active cell balancing. So wherein you can see that makes use of a transformer, right? Of course, transformer, you know, it has got a primary coil. So on the right hand side, you can see this is the primary coil, and you can see the secondary coil is here. So initially the primary coil will be supplied with energy, and you can see that each cell, right, has got a secondary winding with the thyristor here, right? I don't know how many of you know about a thyristor. It's a very fast switching device. It is also called as a silicon control rectifier, shortly SER. So you can see that each cell has got one thyristor. Okay, so when energy is supplied here, you will find that in the primary coil, the energy would be available. Right now, there'll be a sensor that will be monitoring the cell voltage of this particular cell. Let's say take the case of the topmost cell. So if it finds that the voltage has dropped down to less than 3.7 volt, now what happens is less than 3.5 volt. What happens is this thyristor will be firing. Once the thyristor is fired, you will find that the secondary coil of this circuit will get its energy from the primary coil of the transformer. So which means that you will find that now the energy that is available in the primary coil will now be transformed to the secondary winding of the coil, and from there through this you can see that now the cell will get charged. So this will happen, that is charging of the cell will happen as long as the sensor detects a voltage of 3.7 volts. So in this way, you can see that depending on the capacity of the cell, the thyristor will be fired. The thyristor firing will be controlled by means of electronic control unit. Okay, and all these things are on board. All these things are on board. Okay, next slide, please. So this is active balancing. Okay, that's what you can see here. It makes use of a MOSFET. You can see, just read this second point. By switching the MOSFET of the low voltage cell, that particular coil can be made to act as a secondary for the transformer. Okay, next slide. So what is lossless? Now lossless one is lossless balancing. Lossless cell balancing is the one wherein it does not depend much on the hardware. It depends more on the software control. Hence, the design becomes easier and simpler. Okay, this is what I said, and it is this lossless cell balance. Of course, not balancing. Even if you look at the smartphones, what we have today, right? They have better software control, preventing overcharging from taking place or undercharging from taking place. Like for example, if you take the case of mobile batteries, I mean mobile phones, right? Though it will indicate that you have attained 100% charge, you would find that it wouldn't have attained 100% charge. It would have indicated 100%, but it would have charged only 95%. Though it will indicate 0% voltage, but actually there won't be 0%, but the voltage would have dropped down to only a level of about 2.5 volts. So what I'm trying to say here is, the moment the voltage reaches 2.5 volts, mobile phone will be switched off. The moment it reaches about say 3.75 volt, automatically you will find that the charging circuit will be cut off. Charging current will not be flowing in, voltage or current will not be flowing in. That's what I am trying to say. So that's what is called as lossless cell balancing. Next slide, please. Yeah, this is one of the techniques. So wherein you can see that while charging the cells in series, you can see that whichever cell that is weaker, it can be removed by making use of switches. For example, you can see here the cell 5 has become weaker. So while charging, what happens? You will find that the cell 5 will be bypassed. How this will be bypassed? Because the sensor is going to indicate that the cell has become very weak. So automatically you will find that the control unit, right, will cut off the energy supply to this cell number 5. And you can see that after 4, it bypasses and it goes to cell number 6. So in this way, you can see that the damaged cells or the weaker cells can be removed from pack. How this is possible? It is all only by the controllers. It's all because of electronics. Next slide. Next slide, please. Okay, so there are systems wherein you will find that, let us say that we have, in order to understand in a better manner, let us say that we have 2 cells. One is good, the other one is weaker. Okay, if the good ones have been charged fully, now what happens is you will find that the good ones will be transferring the charge to the weaker cell. So in this way, you will find that there will be transfer of charge that will be taking place from good cell to a weaker cell. Thereby, we don't lose energy. Okay, next slide. Yeah, so during discharge also, we need to have the cell balancing taking place. Okay, so we do have systems, right? Again, it is controlled by microcontrollers for balancing, which means that we want all the cells to discharge equal amount of charge. Though it is not 100% possible, but you will find that to a certain extent, yes, today we are able to wake up to a level of about 85 to 90%. Okay, next slide, please. So what happens? You might ask a question, what is there, if we charge, though we don't make use a certain amount of charge in the battery, anyway, we are going to charge and retake. But what happens, each cell has got its own life cycle, meaning that, you can have, let us say, 1 million charging and discharging cycles, right? So if we have too many charging and discharging cycles, the cells will not be lasting longer. Okay, so very frequently you may have to replace the cells. Next slide, please. Yeah, this is what I said. So you can see that when the back to cell balancing while charging, you can see that the good ones will be charging the remaining batteries. Okay, next slide, please. Yeah, this is just, I have taken it from internet. So maybe you can see without balancing, active balancing, you can see that we have active and passive balancing. You can see that all the cells are maintained at the same voltage. When compared to passive balancing, you can see that active balancing can have about 75 to 80% in all the 3 cells. Okay, right, next slide. So we do have, as I told you before, we need to maintain the temperature between 35 to about 45 degrees Celsius. We do have a thermal management block. Okay, so we need to have a battery heating and cooling system as well. Go to the next slide. Next slide, please. Yeah, next slide. So that's what for next slide. So for maintaining the battery temperature constant, right, we need to have both heating and cooling system. Why heating, why cooling? Because we know in certain conditions, like, if you go to Europe or in the US, some few months, you will find that the temperature is very low. So we need to increase the temperature, right? In certain cases, like for example, if you take the case of UAE countries like Dubai, where the temperature will be very high. In such cases, you need to have cooling of the battery so that you maintain the battery temperature constant. So the battery also has a heating and cooling system, which means that the battery component will have a casing with the jackets present in it for making the fluid to be circulated around depending on the temperature condition. Next slide, please. Yeah, so just because temperature is very, very critical for the reactions to take, for the migration of ions to take place between the electrodes. Because this migration will not be taking place properly when the batteries are operated at extremely low temperature and extremely high temperature. Okay, right, next slide. Okay, next slide. Yeah, next we will just briefly touch upon one or two slides on battery charging. Okay, now the other challenging one in the case of electric vehicles is the battery charging. How do you do that? Next slide. Yeah. So you can see that the current and the time, the voltage and the time are given in this figure. So this is applicable even for our mobile phones. You can see that initially there will be more current that will be supplied constantly for about 45 minutes or so. That's the reason why even if you look at our mobile phones, you will find that initially it will be charging very quickly because more current will be supplied until the voltage is stabilized to about say 3.5 or 4 volts. Once the voltage has attained about 4 volts, now what happens? The current will drop down significantly, and thereafter you will find that there will be a constant voltage that will be maintained. Okay, this is what happens even in the case of batteries used in the electric vehicles. So whenever we charge, you would find that initially there will be more current that will be flowing in for charging the batteries very quickly, and once a certain voltage is attained, the current will be cut off. I mean, will be reduced, not cut off, will be reduced, and now the voltage will be increased. So it's all software inbuilt. Okay, next slide, please. Yeah, there are 3 levels of charging as proposed by the United States. So level 1, level 2, level 3, and each one having a different capacity in terms of power, 1.5, 6.6. So the higher the power, the time that will be taken would be lesser, right? Okay, and you can see that in each case the voltage is different, and the source of current is also different. Level 1 and level 2 talking about AC, and level 3 talking about DC, very high voltage, and you can see the current is 15 amps in the case of level 1, and it is double in the case of level 2. In level 3, you can see that it can go up to about 300 amps. Okay, so which means that you can see that the time that is taken when you go for higher power, the time that is taken for charging the batteries, or per hour if you charge the battery, then the range that will be covered will be more when you go for high capacity chargers. Okay, so this is another area wherein a lot of people are working on in reducing the charging time of the battery. So these are the challenges actually. Next slide. Yeah, moving on to the transmission system, probably I think someone asked a question, who owns a car? So I think you must be having a car which should have at least 4 gears, right? So 4 forward and 1 reverse. So maybe for attaining different speeds, you make use of different gears so as to get different torque and different speeds. So usually we have 4-speed or 5-speed gearbox system in a passenger car, right? And in heavy-duty vehicles, it might be about 8 to 14 or even 24 in the case of tractors. But whereas if you take the case of electric vehicle, that is because of the reason that the internal combustion engines can produce very low torque at lower speeds. For example, if you take the case of an internal combustion engine, it can produce a torque of only about 100 to 150 Newton meters in the case of engines employed in passenger cars. But actually, the automobile requires something like about 1000 to 1200 Newton meters of torque, right, for setting the vehicle in motion initially from rest. So which means from 150 to 1200, you need to have a multiplication of this torque taking place in between. From 100 to 1200 Newton meter, which means that you need to have a gear system in between, right, which can have a gear ratio of 12:1, meaning that 100 will be multiplied by 10. So it's a 12, you will get 1200 Newton meters in the wheels, right? So you need a multiple speed transmission system. But if you take the case of an electric motor, so you would find that the electric motor can give very high torque at lower speed. Next slide, please. Can give a very high torque at lower speeds. Next slide, please. Right? At lower speeds, so hence the electric vehicles does not require a multi-gear transmission system. Next slide, please. Multi-gear transmission system, right? But rather a single gear transmission system. Okay. Now the advantage of going in for electric drive is, if you take the case of internal combustion engine, petrol engines can give a maximum efficiency of about 35%. Diesel engines can give a maximum efficiency of about 45%. But you can see that the electric motor can give an efficiency of about 95%. High energy efficiency motors are available today, which can give even more than 95%. Okay, next slide, please. So, since electric motors can give very high torque at lower speeds, so you can see, that's what you can see here, right? So you can see the torque curve is flat at lower speeds, and beyond a certain speed, we are not more concerned about the torque, but we are more concerned about the power. And you can see that the motor can give a flatter power beyond 50% of its rated speed. And the torque is quite high, so hence there's no need for a multi-speed transmission system, unlike in the case of a gasoline or diesel powered automobile. A single gear transmission system is more than sufficient, and there are certain vehicles which make use of two-gear. Next slide, please. Two-gear transmission system. That's what you can see here. This is a transmission system. It's a drivetrain. So you can see the bigger component is the motor. So the motor has a direct drive onto the gears, and this is used in Chevy, GM's Chevy. Okay, next slide, please. Yeah, electric motors. Moving on to the electric motors. Next slide, please. Yeah, moving on to the electric motors. Of course, you all must be knowing that there are three different major variants of electric motors: AC motors, DC motors, and other motors. And out of this, you will find that some vehicle manufacturers are making use of this AC induction motors, a synchronous type also, and other motors like permanent magnet, or even today most commonly employed is, a lot of people are working on this BLDC, shortly called as brushless DC motor, and a lot of research work is going on in reluctant motors, because that is one of the potential motors that has been found to give higher efficiency. Next slide, please. Yeah, this is just to give, you can see that different motors give different efficiency, but all the motors you can see that gives more than 85% efficiency. Okay, next slide, please. Next slide, please. Next slide, please. Yeah, selection of motor, power to weight ratio, because I know weight is very, very important. Torque speed characteristics, efficiency, the cost of the motor, the cost of the controller. Next slide. Yeah, this is This is an electric motor used in electric vehicles. Next slide. Yeah, so you can see that we can have different locations. Maybe what I have shown you here is a truck. So it could be placed in line just next to the gearbox, or maybe it can be placed on the differential, or maybe on the transverse gears mounted. Okay, transfer gears mounted at the central. Next one, next one. Yeah, you can see there's a motor and it has got an inverter also, right? So inverter converts this DC into AC. Okay, so this makes use of a three-phase AC induction motor. Okay, so okay, because we know battery stores only DC, so we need to have an inverter. Okay, next slide. Yeah, another important feature of electric vehicle is that someone asked a question just before. I was making a mention that you sudden application of brake, you lose energy because you have spent energy for making the engine to deliver more power, and suddenly apply the brake, you waste it. Now, what happens here in the case of electric vehicles, since we are making use of motors, this motor can also function as a generator. So at the time of braking, the kinetic energy of the wheels, right, will now be supplied to the generator, right? We know the function of a generator. The function of the generator is to produce electricity, and this electricity could be utilized in charging the batteries. So which means that we are trying to recover the energy. Next slide, please. We are trying to recover the energy, right, which would otherwise be going out as waste at the time of braking, and this energy is converted into electricity. Next slide, please. Yeah. Next slide. Into electricity, right? This electricity is stored in the battery, which could be used later on. Next slide. And such type of braking, next slide. Such type of braking is what is known as regenerative braking. How this is done, how the motor is functioning as a motor as well as generator, this is where again the controller does the job. The controller, during normal operating conditions, the controller will make this motor generator to function as a motor to deliver power to the wheels. At the time of braking, the controller will make the motor to function as a generator for producing electricity. Understand? Next slide, please. Yeah, I just briefly touch upon this electromagnetic interference. Though we talked about everything greenery picture when we talk about electric vehicle, this, that, and all, okay, fine. But there is an issue like electromagnetic interference because of the reason that, today we talk about mostly electric gadgets, many electrical gadgets. And especially in the case of electric vehicles, you'll find that we talk of voltage in terms of about 400 volts and 900 volts. And we have a wiring harness. There are so many sensors, wirings passing here, there, high voltage wire, low voltage wire. What happens because of this? Because we talk about, when we talk about all these things, voltage, current, right? We talk about electricity and magnetism. We talk about electricity and magnetism. So there is interaction. There is interaction between each and every system, and hence we call it as the electromagnetic interference. And in particular in electric vehicle, this will be a very serious issue because we talk about very high voltage and higher current. So we need to have some kind of a system so as to have this EMC called as the, next slide please, electromagnetic compatibility. Maybe I think I will be closing in about 5-10 minutes max, not more than that. I have almost come to an end, come to the end. Okay. Next slide, please. Yeah, I'm not going to get into the detail, just to give we can see there are so many things, right, that gives the electric and magnetic field surrounding, generating, transmitting, usage, and things like that. Okay, next slide, please. So for this to happen, there are a lot of measures those have been taken, and one of the thing is, next slide please. One of the thing is that you place the motor not transversely mounted but longitudinally mounted. Next slide. Longitudinally mounted, not transverse. That is along the axis of the vehicle. Next slide. Next slide. Along the axis, next slide please. Along the axis of the vehicle, the electric motors. Next slide. Next. Yeah, these are some of the sources. Like you have power converters, which will be operating at different frequencies. That will also be transmitting signals. Traction batteries, as I told you before. Next slide. Electric motors, I told you before. Next slide. Yeah, these are all, you can see that Nissan Leaf operating at 400 volts, BMW operating at 500 volts, Tesla operating at 650 volts. So which means that there'll be more of electromagnetic interference in such cases. Next slide. Okay, so we have this EMI problem is overcome by going in for shielded and unshielded cables so as to prevent the interference between the low voltage and the high voltage cables. Okay, next slide. Battery charges. Of course, this is not going to be there on a regular routine, this thing, but this is going to happen only during charging. So, but battery charges also contribute for more of. Previous slide, please. Yeah. What makes electric vehicle very attractive? If you look at this, I have just made a comparison between the gasoline engine, that is petrol engine, with that of the electric vehicle. So you can see that we have unburned hydrocarbon. In the case of gasoline, it emits 0. Or I would say 710 milligram per kilometer. But whereas in electricity, it is only 4 milligrams. Okay. CO, it is 870 milligrams. But in electricity, it is 290 milligrams. NOx, it is 140 milligrams. And in electricity, it is only 5 milligrams. CO2, it is 258 grams, but electricity it is only 133 grams. Next slide, please. You might ask a question that where is the question of CO, HC, CO2, MOX in electric vehicles when we don't make use of any carbon-based fuel at all? I'll come to that in a few minutes. Okay, the major problem of batteries is its density. You can see compared to diesel and gasoline, which are shown on top, it has got higher volumetric energy density, which means that per liter it has very high energy. But whereas you can see that most of the batteries, it is very, very less. That's the reason why we go for a very high, very large number of batteries. Batteries add on to the weight. Battery alone weighs something like about maybe about 400 to 500 kg. Okay, engine weight is almost replaced by batteries. Next slide, please. Okay, so I have just made a calculation. So wherein you can see that if we convert all our Indian automobiles into electric vehicles, we need to have something like about 120 to 150 gigawatt hour of power plant capacity, and which requires an investment of about 120,000 to 140,000 crores. So we can do it in a phased manner. Next slide, please. So you can see that India consumes something like about 252 million tons of petroleum products, investing approximately about 4 lakh to 5 lakh crores of rupees. Okay. Next slide. Yeah. So what is that we are talking about? Okay, India, you can see that I told you still depends mainly on coal for its energy requirements, about 55 to 60%. Okay, next slide, please. Yeah, fossil fuel put together, I told you, we can see 60 to 65%. Rest all it is renewable. Now, when we talk about zero emission vehicles and automobile, do we really talk about zero emission vehicles? No. We will come to that a little later. Next slide, please. Yeah, this is India's vehicle population. You can see two-wheelers. 73% of the total vehicle population is two-wheelers. Next slide. Yeah. I have asked a question, is it justified? What is that? Next slide. Now you can see a man driving a diesel-powered automobile, and the exhaust contains thick, dark, black smoke. Okay? Now the same man is now converting this vehicle into an electric vehicle. See what happens. Next slide. He feels so clean. But where do we get this electricity from? By burning coal elsewhere. I always used to say that when you talk about electric vehicles, stating that, okay, it's a zero emission vehicle, in urban cities, okay, all right. As long as you charge the batteries, making use of the energy that is available, obtained only from renewable energy sources like solar, wind, okay, biomass, or voltaic, whatever, then you can say that it is zero emission vehicle. Otherwise, it is not so. Next slide, please. Yeah, you can see the air pollution from coal burning industrial plant in India. So billions and billion tons of gases are added into the atmosphere. Okay, next slide. Yeah, so what my guessing is that, you know, till 2020, we have been very happily making use of SI and CI engines. Maybe we will go for advanced technologies. Maybe in 21 to 2030, we'll have HCCI and RCCI. And maybe by 30, you will see that, you know, the entire world, I'm just giving at only the world a scenario. So you would find that we will have both the advanced technology engine as well as electric motor, called as a hybrid electric vehicle, or HEVs. Next slide. Though we have a number of hybrid electric vehicles today. And we do not know in future we are going to have totally IC engine eliminated, maybe by 2050, maybe in the entire world. We may have batteries operated electric vehicle as well as fuel cell coming into picture. And later on, you will find that the battery will be totally eliminated and you will have only fuel cell and solar energy coming into picture. And eventually, the automobile will be maybe powered by solar energy, maybe beyond 2100. Okay, next slide, please. Yeah, so to conclude, so you can see that countries like India can implement policies initially to use alternative fuels so as to slow down the great rate of the oil usage and CO2 as much as possible. That should be the near-term goal. And the long-term goal should be move towards a more sustainable transport system so as to achieve near zero CO2 emissions and also to secure sources of energy supply. And as I told you before, I think India should focus more on electrification of these 2 and 3 wheelers, because we know that about more than 70% of the total vehicle population is contributed by 2 wheelers. But in 4 wheelers, it should take a long time, and probably the routing could be, rather than, you know, converting the existing 4 wheelers directly into electric vehicles, maybe we can have an intermediate pathway wherein we can convert that into hybrid electric vehicle and later on move on to electric vehicles. Next slide. Yeah, so advanced strategies converge on hardware and software, whether it is gasoline engine powered or diesel engine powered or electric vehicles. The future automobiles will be only on hardware and software control. So it's going to be more on the control systems. And technologies are evolving in a very, very rapid manner. And like human beings, of course, it's only the smart and intelligent human beings, that makes the automobiles becoming more and more smarter and intelligent. Yeah, next slide, please. Yeah. So in future, cars won't be called as cars, but next one, it's cows. I'm not talking about the bullock carts. We are not going to go back to the olden days, but it will be called as computers on wheels. Next slide. That's computers on wheels. Okay. Yeah. Next slide, please. Yeah, these are some of the references from which I have taken some of these materials. I would like to very sincerely acknowledge these authors for providing me with a lot of source and materials for preparation of the slides, as well as for enhancing my knowledge. Of course, next slide. And I would like to acknowledge these great guys, right? So Robert Kahn and Winsor. Next one. Who are the inventors of, next slide, internet, okay, from which we are able to gather information. Larry Page and Sergey Brin, right, were instrumental in introducing Google to this world. And what is important is the contribution of Larry Tesler, which has made me to make this lecture materials to be prepared so beautifully well. It is the copy and paste technology. So my thanks are due to these people. So I think I have almost done away with. I think I have overshot by about 4 or 5 minutes. Thank you so much for your kind attention and patient listening. Hope I have been able to deliver what I want. In fact, I did not go very deep into it. I thought that I will just give an overall picture of what's happening in electric vehicles and where are the challenging areas. Those are lying for the attention of you young guys. It could be mechanical, or it could be electronics, or it could be electrical engineers. But today, if you look at it, you will find that for an automobile, engineers cannot be working on isolation, right? So every engineer should know about automobile. Electric engineer should know about automobile. Electronic engineer should know about automobile. Computer engineer or software engineer should know about automobile. Likewise, the mechanical and the automobile engineer should know about electrical and electronics engineering. So then only you will find that you will be able to do a very good job. Okay, I think that's all I have. Maybe I would have shared my contact details in the next slide. Yeah, it's time for questions if you have any. Next slide. I have, yeah, you can reach me at either by phone or by email in case if you don't find time to ask question, or if some questions crop up later on, you can always mail me or you can call me for getting clarified. So with this, I close down my lecture. I would like to thank Dr. Malathi and her organizing team and the management of SRM Valliammai for inviting me to share my knowledge and experiences, what I have gained in working on engines and electric vehicles. Thank you so much. If you have any question, I'll be too happy to.
Thank you, sir.
Yeah.
I thank our speaker, Dr. G. Nagarajan, for his elaborative points about green vehicle technologies, modern electric vehicle fundamentals towards online FTP program, global warming and impacts of power electronics towards green technology. We thank you, sir. I request the participants to ask your queries now. You can also type your queries in the chat box. Sir?
Yeah?
Sir, Vijay Lakshmi Sakar asked a question, sir.
Yeah, you can.
The question is, what is the self-discharge rate if SCR is used in balancing the cell?
Oh, okay. One of the significant advantages of a lithium-ion cell is that its self-discharge rate is very, very less. It's just less than 5% when compared to that of any of the other cells what we make use of, which will be about 15 to 20%.
Thank you, sir. Thank you for your answer, sir. Dear participants, if you have any queries, you can post it in the chat box too. Dear participants, if you have any queries, we will continue the session, otherwise I will close this.
Yeah, I think we can close the log off. I think there are no questions.
Yes, sir. Thank you, sir. Thank you for your presentation, sir.
Okay. Okay.
Thank you so much, Professor. Thank you for coming and presenting.
Okay.
Thank you.
My pleasure. Okay. Enjoy.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks.
So I request the faculty participants to join for the next session with 5 minutes break. Thank you.